Hello, welcome back to Learning as a Hobby. I'm going to continue with doing the exercises for chapter 1 in Theodore Shifrin's Multivariable Mathematics in this video. He recommends that you do question 12 and 13. I do want to do a couple other fun problems from the exercise set that you should try to do as many as possible, but question 12 is kind of long, so I don't want to do too many problems in this video. However, I will do one geometric problem and another problem as well, an analytic problem, I guess. So let's do that. Let me bring up the whiteboard. So I guess I'll just do them in order. Question number 7 is a geometric problem. So let me write down what the question asks you to do from the book. All right, so question 7 says, let me just make sure I'm not sitting on the volume button. Okay. So question 7 says, consider parallelogram ABCD. Suppose that AE is equal to 1/3 AB, and DP is equal to 3/4 DE. Show that P lies on the diagonal that P lies on the diagonal AC. And here's the diagram that comes along with it. So we have parallelogram ABCD. Right, and we have a point over here. So this is A, D, C, B. AC is this diagonal. And we also have a point here called point E. And this point here is P, the point P that they're talking about. Okay, and they want us to show that the point P lies on that diagonal AC. So in order to do that, we're going to use the information that they gave us. So this part here and this part here. We're going to have to write everything in terms of side A. Let's see, I think AE and DE, I think either AB or AE and D and either DP or DE. So let's actually do that. For example, AD can be written so AD is actually if this is a parallelogram, so AD is equal to BC. And both of those you can write as AE minus minus DE. So in other words, let me choose a different color. So this leg here this pen doesn't want to write straight. Let me see if I can do that a little bit better. So this side here and this side here, you can write as the sum of this vector with this vector. All right, so that's what I have written up there. And let's see, we can write AE in terms of AB, and we can write DE in terms of DP, but maybe I think I'll leave it like this, AE and DE. Let me leave it like this and see if we might have to go back and forth. So what do we want to show that? Okay, so we want to show that the point P lies along the diagonal AC. So in other words, we want to show that AP is parallel to AC. So let's actually write AP and AC in terms of some common vectors. So let's see, AP I can write as AD plus DP. Okay. And I know that AD is equal to this. So AE minus DE. And also DP I can write as 3/4 DE. So let me just erase this part by this part here. So DP is equal to 3/4 DE. Okay. AD to, okay. So here this gives me AE and minus DE plus 3/4 DE is minus 1/4 DE. And now let's do the same thing with AC. So if we want to write that in terms of, let's see, I want to do it in terms of AE and DE. So AC is equal to AB plus BC. And I know that, let's see, AB is equal to 3 times AE. Do I want to, yeah, let me write it in terms of AE. So 3 times AE. And BC we said was, what was it? BC was AE minus DE. Whoops, this should be plus. Okay, so we get 4AE minus DE is equal to AC. Right, and actually if I factor out a 1, if I factor out a 4 here, I get AE minus 1/4 DE. Or actually I want to show that let me do it the other way around. Or it doesn't matter, I could do it this way. DE. So notice that that AC is equal to 4 times AP. Or in other words, that's the same thing as saying that AP is 1/4 AC. Okay, what that means is that AP and AC are parallel, which means that point P lies along this diagonal. Right, so that's the proof. Okay, so the trick here is to write everything in terms of common vectors. which I'm sure he'll talk about later on when we get to vector spaces and when we talk about bases. But for now, I think that's an interesting problem to include in the first chapter. So that's a geometric problem. Let's take a look at what did I want to do next? I think I want to do number 10. Yeah, let me do number 10 next. Right, I'll write it down for you guys. Okay, so number 10 says this: suppose vector x and y are n-tuples, are non-parallel vectors. Okay, and there's two parts to this question. Part A says, prove that if Sx plus Ty equals the zero vector, then S equals T equals 0. Okay. He gives a hint here, so I'll give you the hint as well. The hint says, show that neither S is not 0, nor T not 0 is possible. Right, and maybe I'll write part B here as well, then we'll just do them one after the other. So prove that if AX plus BY equals CX plus DY, then A equals C and B equals D. Right, that's question number 10. Right, so let's start with part A. Okay, so part A says, prove that Sx plus Ty equals the zero vector, then S equals T equals 0. So these are first off, we're assuming that they're non-parallel, right? So let X, Y in Rn be non-parallel. Right, then if Sx plus Ty equals the zero vector, that implies that, or actually we can say that, assume that assume S without, or maybe I should say without loss of generality. Assume without loss of generality that S is not 0. Right, then we can take Sx and bring the Ty over to the other side, and we can divide by S since it's not 0. And this implies that X is parallel to Y. And that's a contradiction. Or, usually I use that lightning symbol to mean contradiction in my shorthand, but I'll just write this is a contradiction. Right, so that means that if that linear combination is equal to the 0 vector, then both S and T have to be 0. Right, let's do B next. I'll have to do that on the next page. So this is the proof. So again, let X, Y be non-parallel vectors in Rn such that ax plus by equals cx plus dy. Okay, then if we bring everything on to the left-hand side, we get ax minus cx plus by minus dy equals the zero vector. And we can factor out the common vectors. And this implies that a minus c is 0 and b minus d is 0 by part A, which means that a equals c and b equals d. Okay, so that's the proof. All right, that was number 10. And then the next two that he wants us to prove are 12 and 13. So those are the ones he suggested to do in the book. Number 12 has a lot of parts to it. He wants us to basically verify the vector space axioms, but he hasn't defined vector spaces yet. He does that later on in the book. Let me just write down what 12 says. So verify both algebraically and geometrically that the following properties of vector arithmetic hold. Okay, he also says do so for n equals 2 if the general case is too intimidating, but we can do this in general. I will say though, I'm gonna skip doing the geometric proofs of these or verifications of these just because it's relatively straightforward to do it, and I just don't want to waste time doing that because the just doing the algebraic proofs is going to be a long time. So let's do part A first. Part A says to verify for all x, y in Rn, x plus y equals y plus x. So in other words, vector addition is commutative. Okay, so let x, y be in Rn, and x is an n-tuple, y is an n-tuple, and if we look at their sum, by the definition, you add component-wise, and each of these components is a sum of real numbers, and we know that real numbers, the addition of real numbers is commutative, so I can move these around like this. And then I can break this up into a vector sum. All right, so that verifies that first property. Part B says for all x, y, z in Rn, x plus y plus z is equal to x plus y plus z. Right, in other words, this is an associative law for vector addition. Right, so if x and y are n tuples, then again, x is x1 up to, sorry, I need a z in here also. X1 up to xn, y is y1 up to yn, and z is z1 up to zn. Okay, and if we look at x plus y plus z, whoops, I don't need that extra parentheses. Right, this is x1 plus y1 all the way up to xn plus yn plus z1 up to zn, which is x1 plus y1 plus z1 up to xn plus yn plus zn. Okay, and each of the components is a sum of real numbers, and real number addition is associative, so I can reassociate. Right, and then I can break this back up into a vector sum. This is the same thing as x1 up to xn plus, y1 plus z1 up to yn plus zn, which is the same thing as x plus y plus z. Okay, letter C. Okay, the zero vector plus x equals x for all x and Rn. All right, so in other words, the zero vector is the additive identity for vector addition. So if we take 0 plus x, I'm going to skip writing that x is x1 through xn at this point. So the zero vector has n copies of 0, and x is x1 up to xn. This is 0 plus x1 up to 0 plus xn is x1 up to xn, which is the vector x. So that shows that that's true. That was letter C. Right, can I fit letter D in here? Maybe I can squeeze it in. So letter D says for each x and Rn, there's a vector negative x, so that x plus negative x is the zero vector. Right, in other words, there exists additive inverses, so proof. Right, so if x is, let x be an element of Rn, okay, then we know that x is x1 up to xn. Consider the vector negative x1 up to negative xn. We'll call this, let's call this y for now, okay? Then x plus y is x1 up to xn plus negative x1 up to negative xn, which is x1 minus x1 up to xn minus xn, which is the zero vector. Okay, and that shows that every vector in Rn has an additive inverse. Okay, that was letter D. Letter E says for all C, D, and R, C times dx is equal to C dx. Okay, so if we take C times dx, this is C times the vector dx1 up to dxn, which is the same thing as C times dx1 up to C times dxn. And again, a multiplication of real numbers is associative, so we can reassociate C dx1 up to C dxn, which I can factor out the scalar, which is CD times x, right? That's letter E. Letter F, which I guess I'll do on the next page. Letter F says for all C and R, and X, Y, and Rn, C times x plus y equals Cx plus Cy, right? Sorry, my thumb's falling asleep. Okay, so proof. So let's take C times x plus y first. Right, this is a distributive law for real numbers, so this is Cx1 plus Cy1 up to Cxn plus Cyn, which I can break up into a vector sum. And I can factor out the scalar multiple. Which is Cx plus Cy. Okay, letter F is done. Letter G is just two more of these. G says for all C, D, and R, and X and Rn, C plus D times X is Cx plus Dx. So kind of distributive law. Proof. Let's start with C plus Dx. Right, this is C plus D times x1 up to xn. And by the definition of scalar multiplication, get this, and there's a distributive law for real numbers. Then I can factor out the scalars. Which is Cx plus Dx. Okay, proof is done. And then letter H says for all x and Rn, 1 times x equals x. Right, so there's a kind of multiplicative identity for scalar multiplication. All right, so 1 times x is equal to 1 times x1, all the way down to 1 times xn. And 1 is the multiplicative identity for real numbers, so we get x1 up to xn, which is x. Okay, so that verifies, these are called vector space axioms. He doesn't say that in the book, but this verifies all of the axioms, okay? There's one last problem that he suggests to do, which is 13, so I'll finish up with that one. I think there's 2 parts to this one, but they're relatively quick to prove. So A says, using only the properties listed in exercise 12, the one that we just did, prove that for any x in Rn, we have 0 times x equals the 0 vector. Okay, and then he says, there's something right after it. He says, it often surprises students that this is a consequence of the properties in exercise 12. You can tell me whether it's surprising or not, but we'll prove it. There's part B also, but I guess I'll just prove them one at a time here. So proof. All right, so we want to show that 0 times x is the 0 vector, so I'll start with 0 times x. And we know that 0 is the same thing as 0 plus 0, which is, which rule was it that we did? This one here by part G. This is the same thing as 0x plus 0x. Okay, so we get the equation 0x equals 0x plus 0x, whoops, 0x. And we know that additive inverses exist by, what rule was that? This is the associative law, identity. Where did I do the inverses? Oh, I think, did I do it on the same page as one of them? Oh, over here, sorry. Yeah, this was the one. So there, every element has an additive inverse. So by that one, we can take, on the left-hand side, we can take minus 0 times x plus 0 times x. And same thing on the right-hand side, there should be an equals here. Minus 0 times x plus 0 times x plus 0 times x. And here I can reassociate. Right, and when you add additive inverses together, you get the 0 vector. So on the left-hand side, we get the 0 vector, and on the right-hand side, we get the 0 vector plus 0 times x. And 0 plus anything, since it's the additive identity, we proved that in, let me just look in the book, what that was from part C. This gives us that 0 vector is equal to 0 times x. Right, so that proves that property. Right, and then part B says, using the result of part A, prove that Negative 1 times x is negative x. And it says, he says after that, be sure you didn't use this fact in your proof of part A, okay, which we didn't. So let's finish up with that one. Proof. So what we want to show is that negative 1 times x is the additive inverse of the vector x. So let's take the sum. So consider x plus minus 1 times x. Right? I can factor the vector x out by using one of the properties that we just did in question number 12. It was one of those distributive laws. 1 plus minus 1 is 0. And we know that 0 times x is the 0 vector by the last thing that we did, part A, right? Okay, by part A. So we get the equation x plus minus 1 times x is the 0 vector. And then we can add the additive inverse of x to both sides. So we can take negative x plus minus 1 times x equals negative x plus 0 vector. And I can reassociate on the left-hand side. Okay, and on the right-hand side, anything plus the 0 vector is just that thing. Okay, and on the right-hand side, negative x plus x, since they're additive inverses, that gives you the 0 vector. And 0 plus anything doesn't change anything. So this says that negative 1 times x is the additive inverse of x, and that's it. Okay, so those are the proofs from chapter one, the problems from chapter 1 that I wanted to do, or actually, part 1 of chapter 1, because I think there's several parts in chapter 1 here. We did part 1. Chapter 2 is on the dot product, so I'll get to the notes for that relatively soon, maybe even today or tomorrow. Chapter 1, yes, we did chapter 1, part 1. So next we'll do dot product. All right, guys, so let me just stop the screen share. All right, so that was the exercises for, again, I didn't do all of them, but we did the ones that he suggested, and I did a couple other ones that I thought were fun. So we'll continue with chapter 1, part 2 next time. All right, and keep an eye out for the part 2 of the exercise set for Spivak chapter 2. That'll be coming up this weekend as well. All right, see you guys then.